Okay, so big picture. What are we doing in this course right now? What are we doing in this class right now? This is what we're working on. You know how fast a quantity is changing at every moment? You want to know how much of it you have at every moment. You know how fast a quantity is changing at every moment? You want to know how much of it you have at every moment. So, how would we know how fast a quantity is changing at every moment? What would we have? What would we have in the back? What would we have that we would know how fast a quantity is changing at every moment? Okay, so yeah, a rate of change function. Okay, a rate of change function. So like in your quiz, this was what? The rate of change of the plane's height, right? The rate of change of the plane's height for six seconds, right? 6 seconds since it went out the window of a building, okay? So there it is, rate of change, okay? And so in order to get what we want in the end is what? What is how much of it we have in this example? How much of it we have would be like the height of the plane or the accumulated changes in height, right? So it's accumulation of height from time equals 0 or just its height above the ground, okay? That would be what we mean by you want to know how much of it you have at every moment. So the accumulation of height, or the height of the plane, the height of the plane. Okay, so we have to do this, to achieve this, we have a succession of functions that we work through. This is on the second exam. This, what I'm about to tell you, is on the second exam. There's a succession of functions that we work through to get from the rate of change function to the accumulation function. So we start with the exact rate of change function. That's the first thing that we have. That's knowing how fast the quantity is changing at every moment. What function do we build from that as the next step in the progression? Someone said it over here. Approximate rate of change. We take this exact rate of change and we build an approximate rate of change. How do we do that? We decide the width of a moment. We decide the width of a moment. In your plain example, it was 2 seconds. The width of each moment was 2 seconds. And then we use the actual rate at the start of the moment to be a constant rate for that whole moment. That's the left approach. We use the actual rate at the left side of every moment to be the constant rate for that whole moment, and that people are on their cell phones. All right, so that would be, and when we put all those constant rates together in each moment, that makes up the approximate rate function, what I have there, and we just call that R. So the exact rate function, our notation is R sub B. For this particular problem, B. Okay? Then the approximate rate function is just little r. Okay? And from the approximate rate function, we can build what? What's the next one in the succession? That's what we're working on. From approximate rate to build approximate accumulation, or approximate net accumulation. Approximate net accumulation. And so here's what that looks like. Oh, shoot. Spoiler alert. Okay, so approximate accumulation. Approximate accumulation. So this is net accumulation because it's tracking the change from the starting height. How much was the change from the starting height? So approximate accumulation will always start at 0. Y equals 0. It will always start at the point 0, 0 because the change from 0 is 0. And so this is tracking how much did the height change? How much did the height change from time equals 0? All right, so in the first 2 seconds, what happened? The rate was -7. We calculated it was -7. And so in 2 seconds, we get the change in accumulation by m dx, right? M dx, or in this case, MDX, so -7 times 2. So in those first 2 seconds, it lost 14 feet because the rate was -7. Over 2 seconds, it would lose 14 feet. So that key point there at the end of the first interval is 2 seconds and negative 14 feet, right here. How can the height of the plane be negative 14? Is it underground? No, what does that negative 14 mean? Change from its starting height. Change from its, that's what we mean by the approximate accumulation, that accumulation function. It's tracking changes from starting height. So with a negative rate of change of negative 7 over 2 seconds, negative 7 times 2 is negative 14. So by the end of those 2 seconds, it's at negative 14 feet from the starting height. Okay? Similarly, in the next, we can get the change in the next interval, which would be the rate is negative 3 for another 2 seconds. Negative 3, the rate, times the change of 2 is negative 6. So we get a change of negative 6 in the second interval. And then y final equals y initial plus the change. Y initial is negative 14. The change is negative 6. So y final is negative 20. So now, negative 20 is over those first 4 seconds. Its approximate change in height was negative 20 feet. And then likewise, in the last, so that is y final for the second interval, but then it becomes y initial for the next interval, right? So now it's where we start in the next interval. And so we go negative 20, what? Plus the rate is 9 times 2 is 18. So we got the point 6, comma, negative 2. Almost made it back up to its starting height. Okay. So negative 20, starting accumulation plus the change, which would be 9 times 2, 18, gives the final net accumulation of negative 2. Okay, so then we could build that function as our a sub x function. From 0 to 2. Each one of these formulas is just initial plus the change gives the final, right? So the initial is 0 plus the change is negative r. Yep. So if you wrote r of x, that's fine. I'll just write the number, negative 7 times. So what is any change in the first interval? Any change in the first interval would be x minus 2. Were they t's or x's in here? The x's. Okay. Yeah. So any change in the first interval to any value x would be x minus 2. 0. X minus 0. I was just testing you. Okay. So now, and we know that now by the end of the first interval, we've accumulated negative 14. And so we go that becomes y initial. Y initial plus the change is m dx. So we got m. Now what's the change in the second interval? X minus 2. Okay? And finally, by the end of the second interval, we know we've accumulated negative 20 feet of height. So that becomes our y initial for the third. Y initial plus the change in y is the rate times the change in that interval. So for any x in that interval, the change in that interval is x minus 4. If you defined Rx first, you could have defined Rx as negative 7, negative 3, and 9, and then you could just written Rx there, because the Rx function gives you those values: negative 7 for that interval, negative 3 for that interval, 9 for that. So if you define Rx and then just put Rx there, that's great too, right? Because AX, our net accumulation function, is built from the approximate rate function. So That's why Rx, Rx, Rx shows how AX is being built or created from, or AX, A of X is being created from R of X. So what, right there, that's R of X, right? Questions on the net accumulation function? It's tracking the net accumulation of height as time goes by. Because the rate starts at negative, we're losing height, and then it's going back up. Yes, sir. R sub B, or R? Well, let's see here. Only if you define the R values as less than or equal to on this side, and we haven't been doing that. If you did that, if you put the equals on this side, then yes, it would be R of 2. But the point is that R of X is giving us the rate function the whole way. So it's the best thing to do is just write R of X. Because for any value of X, it's giving us the rate at that value of X. So that, we didn't just build R of X for nothing, right? Was there another question over here? Okay. But if you did strictly less than for your R function, then that won't work. What you said won't work. But talk to me after class. You'll see that. Yeah. But the best thing to do is to build the function R of X, -7, -3, 9, and then just use Rx. So for any value of X, you're getting the rate that you want in every interval. Okay, so we're talking about the succession. First comes, in this process of, you know how fast the quantity is changing, you want to know how much of it you have. First function is, what kind of rate of change? Exact rate of change. At every moment. That's exact rate of change. We build approximate rate of change. It's on the test. It's just on the test, exactly what I'm saying. Okay? Approximate rate of change. From approximate rate of change, we do approximate net accumulation, or approximate accumulation. That's what you built there. And then the last, what was our goal all along? Which we haven't done this part yet, but we know the goal is exact. So exact net accumulation. Exact net accumulation would look like that. So we call that one capital A of B, right? So the subscript is indicating exact functions. R sub B, exact rate. A sub B would be exact net accumulation. Exact net accumulation. That's the one we want. We don't want an approximate. So see how bad, especially around 5 and 6 seconds? See how bad our approximation is. Why? Because we use really big intervals. But we want the real one. We want the exact net accumulation from exact rate. So one more time. Exact rate of change. We build approximate rate of change. And we build approximate accumulation. And then the last step we haven't got to yet. How do we get exact accumulation? Okay. Now the last question on your quiz was about what would the height function look like? Just the plain old height function. How would that, or the total accumulation, right? The total accumulation versus net accumulation, what would that be like? So at 0 now, total accumulation is not 0. What's total accumulation at 0? 50. So at 0, it'd be 50. So now I'm not, in yours, it asked about the total approximate accumulation. So I'm going to show the total exact accumulation, which would be that exact net moved up 50. And that would just be the function B. So B is our quantity function, right? So with the rate of change of B, we have the net accumulation changes from 0, and then the actual quantity, which would be like height above the ground of the plane. Starts at 50, dips down, and then heads back up again. Okay, but the key is the 4. The first 4 that we talked about. So either A sub B or B could be like the fourth one, right? So we want it's exact accumulation, whether that's net accumulation or total accumulation. Okay? Exact rate, approximate rate, Approximate accumulation, exact accumulation. That's the journey we're on, okay? And I think I touched on everything in the quiz. Any more questions about that? Okay, so you've got, let's see. You read, over the weekend, you read about the rocket-powered basketball. Is that right? A little bit? Someone said no. Did you? Right? Yes, you should have. You should have. So we're going to talk about that. So we're on to this next. So we got this basketball, right? It's rocket power. Rocket power. I think I did. Yeah, didn't I start? Yeah, we're going. Okay, and so rocket power. So why would you want to rocket power a basketball? No, because we need to send it to Pluto to regain its planet status, right? Of course. All right. So we've got this, and on the left, I've got a graph there, and it's this velocity, meters per second, and time in seconds. Okay, what kind of function is V? Is it rate of change or accumulation? Velocity in meters per second will be rate of change, right? So this will be rate of change of what? Rate of change of what? But basketball isn't a quantity. Basketball is a thing. Rate of change of, that's the units, the height, right? So it's the rate of change of the height. So the meters, which is the rate of change of, the numerator of that unit would be meters for the height, right? Okay, so that the independent quantity is our horizontal, that's time since launch. And then the dependent quantity is, of V, is the rate of change of height, all right? So V is the rate of change function, relates the velocity of the rocket to the time elapsed since launch, okay? All right, we wanted to develop the accumulation function associated with V. What are its independent and dependent quantities? So what's the independent quantity for an accumulation function for this rocket basketball? Independent would be? Still, it's the same exact quantities we have for the rate of change function. Time in seconds since launch. Dependent quantity is? So it's talking about accumulation. So it could be, you could say net accumulation of height, but if it starts at zero, if it starts at height 0, then the net accumulation of height and the total accumulation of height would be the same. But maybe the net accumulation of height is the change in height from 0, and then maybe it's launched from a platform, that's not on the ground, and so then the total accumulation will also have that height of the platform in there. Okay. So we want the height of the rocket as a function of time elapsed. Okay, that's our accumulation function, accumulation of height. Okay, so I want you to just take a minute or two to work through these questions. So think about them yourself, and then work with the person next to you. Okay. Question 3 is the big one. Can we get it? The answer to number 3 is not, it's the rate of change. What does that mean? That it's the rate of change. What does it mean? V of 5. So yes, what does V of 5, the rate of change, mean for values associated with the accumulation function? This is the important question that we've been working on for the whole semester. Okay, so on the back of this sheet that we gave you, on the blank side, write out your answer to number 3. Write up on the black, write it out in words. Everyone should have one close by. Just on the back, write out your answer in words to number 3. Or in your notes, even better. So just, if you're taking notes, then yes, put in your notes. Okay, so coordinates of the point. 5 comma V of 5. And that's the point I highlighted there. That's the point I highlighted. Okay? What does the value of V5 represent, and where do you see its value on the graph? What does its value represent? Yep, so it's the, yes, It's the rate of change of the rocket's height at the moment t equals 5 seconds, right? So it's the velocity at t equals 5, and we know that that means that that's that rate of change in a moment at t equals 5. Where do we see its value in the graph? Okay, good. So yeah, we don't see its value at this point. This point is both values taken together, right? That's a correspondence point of two values taken simultaneously. V of 5 would be somewhere like here. Thank you. Yeah, got it. Thanks. Okay. All right. So up here. Okay. So that's V of 5. And so that's the rate of change of the rocket's height. And so what does that mean? What does that mean that it's the rate of change of the rocket's height? Volunteer from the back. Anybody from the back want to volunteer to read what you wrote? Yes, please. So that was a very true statement, but all in all, you just basically said it was the rate of change. So yeah, that's true, but kind of in a nutshell, you said it was the rate of change. What does the rate of change mean? Well done, well done. The change in the height of the rocket is v of 5 times the corresponding change of time. But like you said, in the moment, in a moment at t equals 5, and symbolically, how do we have that? Symbolically, what do we say? dh equals v of 5 dt. dy equals mdx. dy is the same as dy equals mdx. But now the change in height, if you said dy, that's fine. We never defined h. I'm just using h. dh equals v of 5 dt. Okay, so this is this huge theme. Changes in the dependent are the constant rate times the change in the independent. Now this only works for in a moment, right? Because if we're at 5.5 seconds, we have a different rate, right? It's a different rate because the rate is continually increasing. So it's got to be in a small moment. This only holds true within a small moment at t equals 5. Okay, questions on this? Kind of just getting ourselves oriented with the situation. Okay. So now take a look at your paper. So what kind of function do we have? We have exact rate of change, right? Exact rate of change of the height of the rocket. And so first I want you to highlight points on your graph at every 0.9 seconds. So starting at 0, every 0.9 seconds. Okay? And this is defining our moments, right? So it will define our intervals. Our big moments, right? Our big moments, 0.9 intervals. Okay, and so here's where we're going to introduce this notation delta t. Maybe you read about it, okay? Delta t, as opposed to dt, delta t we're going to define as the width of a moment. The width of the moment is delta t. And so by highlighting these points every 0.9, delta t is the width of the moment. So is delta t a variable or a parameter in this situation? Is it a variable or parameter? We got one down here saying parameter. Agree? Right, because we're going to set it. We're going to set it at 0.9, and it's not going to change for the given situation. We're going to set it at 0.9, and it's not going to change for the given situation. Okay? So our delta t of 0.9 is a parameter. So after you've highlighted those points, you're going to sketch the approximate rate function on the graph we gave you, and that's just r, right? The same way we've been doing it. You're going to use the actual rate at the left side of every interval to be the constant rate for that whole interval. You're going to use the actual rate at the left side of each interval to be the constant rate for that whole interval. So this should be familiar. We've done it a few times now. And that's building, you're drawing the new function R, right? You're drawing a new function that we call R. So the given rate function, exact rate, R sub h, and then the approximate rate you're building from that is just R. Compare with the people next to you. Yeah, and then if you want to also define it, okay, you never drew the function. So you're drawing, right? So you're going to sketch the approximate rate of change function. I'll just show you. Yeah, so you're sketching the approximate rate function, and then when you're ready, you can define it down below. And you can write out its definition below. The exact rate function is R sub h. R sub h. That's the exact rate function. Or B. No. R sub h or B. B. So two names for this function. The exact rate is either B or R sub h. Either one. Those are both what we're using for the exact rate. Approximate rate is just plain old R. Don't do anything else. You're just working on the rate, just on the approximate rate. Okay, anybody have a question on that much? That much. Any questions? Okay, so it should. Geez. So now that we have, okay, so we're taking our exact rate function, we're making this approximate rate function. So we're making it worse, right? So it's this now is only approximating the rate when we had the exact perfect rate. Why would we do this? Why do we make it worse? Key point. Why are we making it worse? Why are we taking what we had that was exact and making it non-exact, making it approximate? We want constant rate of change. Constant rate of change. We've been working on it for the last month because that math is doable and easy, right? We can get changes by the constant rate times the change in x, and those changes represent a part of the accumulation, right? By getting a change in height from the constant rate of change, we're building an accumulation function. Okay, we're building changes, and then doing y final equals y initial plus the change, right? And that builds those are the tools that we build the accumulation with. Okay. All right, so you just built your approximate rate function, R, which I've got in black now, okay? And so R sub H or V, one and the same. So now I'm actually giving you that that function now is t to the 1.3. Okay, that rate function is t to the 1.3. So you've done R of t, right? Has everyone done R of t? So you could use R of H of 0, or you could use V of 0. But what you can't do is you can't use R of 0 because you're making that function. It doesn't exist yet. You're creating the R function, and it's built from the exact rate of change. So you could have V of 0 there or R sub H of 0. Those are the same, right? So we're building approximate rate from exact rate. So does your first interval look like that? And if you have R sub H of 0, that's the same thing. They're both the same. So what will the next constant rate be? V of 0.9. So for the second interval, we want the constant rate that's the exact rate at the beginning of the interval. V of 0.9. And so on. That's good. Question, please. Yeah, so for instance, in the third interval here, how are we determining in the third interval? So we got a constant rate in the third interval. Where's that constant rate coming from? So right here. So there's some rate here that we're choosing to be the constant rate for that third interval. Where does it come from? Obviously it's not 0. Oh, you want to try to average it and do that in the middle one. But so we want a systematic way of doing this, so when we do it, we all do the same thing. So you looked up and said, oh, it looks like it's about 1. Well, someone else is going to say, oh, it looks like about 0.8. And someone else will say, oh, it looks like 1.1. Constant rate of change. This is the whole point.
It's just an approximation, that's all. It's just rough, so it doesn't have to mimic it perfectly, that's all. I think he's getting confused because the rate of change is not 0, but our approximation is going to have.
Yeah, so in that first, okay, but we're just following the system. But you could say that about what you just said. You could say that about any interval. Don't get hung up on 0. You could say that about any interval. Well, look over here. When I get to the end of this interval, wow, it's way up here, but we're calling it way down here. It's the same thing. It's just that you're getting hung up on the value 0. Okay, so that was what I was originally engaging you with. Look at this third interval. We've got a constant rate of change in this third interval. Where does that value of constant rate of change come from? How did we get it? What's that? Which was what? That's right. Which is what? Yeah. On the left side of the interval. Right. Yeah, so that you're using the x values on the left side of every interval to be the constant rate for that whole interval. No, it's okay. It's okay. So I don't know. So something about the first interval. What's that? Yeah. Yeah. Right. Right. Okay, so it's better? Okay, cool. So now we've got all these constant rates via a rate function. So then now we want to build the accumulation function. And so we've done this a few times in the last week or so. Okay? So you're ready to go. So, but here's the thing I want to show you with this. So we can avoid actually having to calculate all these accumulations along the way. So what's the first one going to be? It's going to be, what's our accumulated starting height, or starting accumulation height? 0. So that's initial plus 0 plus the rate, which is what? Sorry, what's the rate? The rate is R of t. We're going to use our approximate rate function now. We're going to use the approximate rate function. So it's 0 plus R of t times the change in the first interval, t minus 0. Yeah, please. Yes, but then we did this all for nothing, right? So let's use the RT. So we want to build the accumulation function from the approximate rate, which is the R function. So let's use it. Let's use it to do that. But you're absolutely right. RT is the same as V0. Yeah, you're right. Yeah. This is for this interval, right? It's for this interval, right? So only when t is in this interval will it use RT in that interval, which will be the V of 0. Yep. Okay, so here, now I'm going to show you something. Rather than figure out what the accumulated change was in that first interval to use right here as the starting of the next, look what we can do. And so because we said it was equal to 0.9, how can we represent that starting amount? He wants A of 0.9. Does that represent the starting amount in the next interval? Which we've already defined in this first line, so it's okay to use it. It's already been defined. So instead of doing the calculations, we could just represent it as A of 0.9. And that's why, so last class we talked about, that's why we're putting the equals on the right. So that we can grab that A value that we just found at the end of the last interval and make it the starting A at the next interval. And we can just represent it, and we don't have to do all the arithmetic. Okay, so can you finish now? Can you finish? So that line's not done. Can you finish the A function maybe just for 3 or 4 lines? See if you can do it. Any questions? We got one more thing to do. I put it all up. Any questions? Okay. So the only thing new here is that I'm using the function A recursively. I'm by putting the equals on the right side of every interval, I can pull that last value and represent it as, say, A of 3.6 to be the starting accumulation in the next interval. So that's really the only difference here than what we've been doing recently. Okay, so now, what's the meaning of a of 5, and how does the function determine its value? So what's the meaning of a of 5? The meaning of a of 5 is the net accumulation of height 5 seconds after launch. The net accumulation of height 5 seconds after launch. How does this function find a of 5? What does it do? Right. It's going to come here. When t is 5, this line applies. It's going to plug 5 into that line because 5 is between 4.5 and 5.4. And when it does that, so here it's going to calculate what? The change in that interval up to 5 times the constant rate in that interval will give us the little change. Plus what? All the accumulated change from before. So to do that, now so it's going to go back to the previous line and plug in 4.5 and compute that, etc. Okay? So that's how it does a of 5. So where we're going here, so this is, hold on, so just, might be a minute or two over today. Where we're going is, we want to be able to write this function in one line, one rule. Not one for every interval. We want to be able to come up with this a of t function with one rule. That's good. That's our goal. Okay. So we're going to kind of change gears in terms of we've done this enough times now. Built this a of t function this way in pieces. We're going to start working on how would we write that a of t function in one rule. Okay. And so let's think about that. Calculating that value a of 5 in a new way, okay? It's not really new, but so let's find the approximate height of the rocket. That is a of 5. We want to use the same r function that we built, the same approximate rate, but just with direct calculation, not plugging it into a, the a that we found. We just want to do a direct calculation. What would that be like? If we just wanted to find, and I'm showing it right there on the left. I'm showing it. We want to find what? So we've up until that point, we've had all these constant rates over the intervals of 0.9, and then we've got this constant rate, and so then at 5, how could we just directly calculate what the net accumulation is at 5? Well, there's kind of two things going on there. We could consider all the changes in height accumulated within the completed delta t intervals. How many were completed before that? 1, 2, 3, 4. So it happens to be the same number. But there were 5 completed intervals before we got to t equals 5. Did you see that? And then there's a little bit more in what we call the current interval. Okay, so those are the completed intervals. And then there's a little bit more accumulation in the current interval. All right? So we want to compute that value of a of 5 just directly. So we just want to what? Add up all the accumulation from the completed intervals, add a little bit more accumulation from the current interval, and add it all up. Right? Add it all up. So could you write out an expression that would do that? So we want to all the accumulation from the completed intervals plus a little bit more from the current interval. How do you get the little amount of accumulation from one interval? How are we going to calculate from one interval? What is it? No, not final minus initial. Yeah, so how do we do it? How do we calculate the little change from each interval? MDX, right? You've got the rates from R, and then what's dx? Dx is now delta x. It's just that width every time. So it's just MDX. First rate times change in t. Second constant rate times change in t. And every one of those changes in t is 0.9. Okay, where does that last interval end? 4.5, right? So I want you to find the little bit of change from the current interval. What would you write to express the little bit of change you get now in the current interval? What would that be? No, the change in height. The change in height. So what change in height would you get from the current interval? How would you express that? Times what? Yeah, that's it. Right? Because it would still be the rate at the left side, the v of 4.5. Okay? But now here's where dt comes in. Remember, dt is the change within the interval. So in the current interval, we have dt is 0.5. So we have our completed intervals, which are all of width delta t 0.9. And then in the current interval is where our dt is. And that dt is not 0.9, but 0.5. It's the distance from 4.5 to 5. So we would add all that up. So that amount of accumulation at 5 is what? It's shown right here. It's the sum of accumulation from completed intervals plus a little bit more, right? Plus a little bit more, which is the accumulation from the current interval. This is a really important idea for building that one line, that one rule accumulation function. That's the idea of that one rule accumulation function. The sum of all the accumulation from completed intervals plus a little bit more accumulation from the partial interval or the current interval. Okay. I'll try to give you back the time another day.